In 2017, the door opened a crack. We saw Oumuamua. It was a tumbling, dark, cigar-shaped enigma that defied explanation. In 2019, the door swung wider with 2I/Borisov, a ghost from another world that looked surprisingly like our own comets. We thought we might wait decades for the next one. We thought the galaxy was vast and empty, and that these interstellar interceptions were once-in-a-lifetime events. We were wrong. It is December 14th, 2025. 2 weeks ago, the Hubble Space Telescope turned its massive mirror toward a patch of sky that, to the naked eye, looks completely empty. What it found there is currently rewriting the textbooks on planetary formation. Today, we are doing a complete pixel-by-pixel breakdown of the first high-resolution image of Comet 3I/Atlas. The letter I stands for interstellar, and looking at the raw data, I can tell you this visitor is not like the others. So grab a drink, sit down, and let's put this on the big screen. We need to talk about the scale of what we are looking at. Before we dissect the Hubble image, we have to understand how we got here. Just last month, the ATLAS survey, which stands for the Asteroid Terrestrial Impact Last Alert System, pinged an object moving way too fast. We're talking about a hyperbolic excess velocity that made it mathematically impossible for this object to be orbiting our sun. It wasn't an ellipse, it was a hyperbola. It came from the void, it's swinging by, and it's leaving forever. Now, usually when we spot these things, they are faint, fuzzy dots, but 3I/Atlas is bright, surprisingly bright. This gave astronomers a very narrow window to request discretionary director's time on the Hubble Space Telescope. And that brings us to November 30th, 2025. The image you are analyzing today was taken using the Wide Field Camera 3. This is the workhorse of Hubble. It's the camera that has given us the pillars of creation and the ultra-deep field. And on that cold November day, it stared into the darkness to catch a traveler moving at over 100,000 miles per hour. At first glance, it looks like a standard comet. But let's look closer. There are 3 specific anomalies in this frame that we need to address. First, look at the background stars. You see those lines? They aren't point sources. That tells us everything about the mechanics of this photo. Because 3I/Atlas is moving so fast across our field of view, Hubble couldn't track the stars and the comet at the same time. The telescope had to lock on to the comet's nucleus. The length of those star trails corresponds to the exposure time. This wasn't a quick snapshot. Hubble had to open its shutter and physically pan across the sky to keep the comet centered. This is a visual representation of pure kinetic energy. Second, look at the filter information. The metadata reads F350LP. This is crucial. This stands for a long-pass filter starting at 350 nanometers. Why does that matter? 350 nanometers is right on the edge of ultraviolet and visible blue light. The fact that the comet is so prominent in this filter tells us about its chemistry. We are likely seeing strong emission lines from cyanogen and diatomic carbon. When sunlight hits the ices on this object, it rips molecules apart, and as they decay, they glow blue-green. This confirms that 3I/Atlas is rich in volatiles. Unlike Oumuamua, which was a dead rock, this thing is alive, it's venting, it's breathing. Third, don't be fooled by that bright white dot in the center. That is not the surface of the comet. That is what we call the false nucleus. The actual solid body, the iceberg itself, is buried deep inside that glare. Based on the brightness, we estimate the core is small, maybe only a few kilometers across, but the cloud around it, that's where things get scary. This is the part of the image that kept me up last night. Look at the bottom left corner where the scale bar is located. It reads 30 arcseconds. Now, arcseconds are a measure of angular size in the sky, but because we know the distance to the comet, Hubble astronomers have calculated the physical size for us. It represents 25,830 miles, or 41,570 kilometers. Let that sink in. The diameter of the Earth is roughly 7,900 miles. That means this scale bar, this tiny corner of the image, is more than 3 times the width of our entire planet. Now look at the blue haze, the coma. It extends well beyond that scale bar. We are looking at an atmosphere of gas and dust that is comfortably larger than Jupiter, generated by a rock the size of a small town. This is sublimation on a massive scale. It implies that wherever this object came from, it was cold, absolute zero cold. It has likely been in deep freeze for millions, maybe billions of years, and this is the first time it has felt the warmth of a star. We are watching the primordial skin of an alien solar system boiling away right in front of us. If you look at the direction of the tail, notice how it fans out to the right. This is the pressure of sunlight literally pushing the dust away. By measuring the angle of that tail, we can calculate the size of the dust grains. And here is the preliminary rumor circulating in the scientific community. The dust is fine, like smoke particle fine. If the dust was heavy and rocky, the tail would curve differently. This straight, diffuse push suggests the material is incredibly primitive. We might be looking at pre-solar grains, dust that existed before our own sun was even born, carried here inside this icy traveler. So what does this image tell us? It tells us that the galaxy is not empty. It tells us that solar systems are messy eaters. They eject trillions of these icy rocks into interstellar space. We are drifting through a sea of these ghosts. Hubble has done its job. It has given us the map. Next week, the James Webb Space Telescope is scheduled to point its near-spec instrument at 3I/Atlas. Hubble gave us the picture. Webb will give us the ingredients. We will know if there is water, if there is methane, and fingers crossed, if there are complex organics. We are living in the golden age of astronomy, my friends. 3 visitors in less than 10 years. We aren't just looking at the sky anymore. The sky is coming to us. I'll be doing a live stream when the Webb data drops, so make sure you are subscribed and have that notification bell turned on. You do not want to miss the chemical analysis of this thing. Let me know in the comments, if you could land a probe on 3I/Atlas, what would you want to find? As always, keep looking up.